Hey everyone, in this video we're going to talk about transforming functions. And the goal would be being able to transform any function from a graph, even if it's something crazy looking, like this random arbitrary function f of x here. Okay, so what we're going to do is look at the transformation rules and see how they can apply to any graph. So starting with number one, you see a function rule for g of x. And it says to get g of x, and this is where it might look different than your regular equation. Okay, so you'll see an f of x in there, but it's really f of x plus 2. Okay, so instead of looking at this like an equation where you have inputs and outputs, I want you to think of this as a function rule. Okay, and this function rule says to get g of x, you're going to take the function f, which this is just defining the function we're using this graph. Okay, so you're going to take the function f. Okay, you're going to take the x values and add or subtract a number to them, and you are also going to add or subtract a number to the outside of the function here. Okay, so instead of, again, looking at this like an equation, you're going to look at it like a rule. And what I'm going to do is I'm going to first define what each rule is. So first, when you see plus or minus, you should be thinking of the word translate. And translate just means to slide. Okay, reason being, if you take one of your coordinates, whether it's x or y, and you add or subtract a number to it, it's going to move the location, right? If you take this y value is 8 and add 2 to it, you're up here, you've slid up 2 units. That makes sense. Okay, now to be more specific, there are two different transformations happening here. First, you have x plus 2. Since it's directly attached to the x, this is going to be a horizontal translation. And maybe let's branch that off of translate. And it's going to be horizontal or on the x-axis. Okay, that's the plus 2, because it's directly attached to the x. Now, this minus 3 here, this minus 3 is attached to f of x, or to the function as a whole, which we know that y and f of x are kind of like saying the same thing. So it's really attaching the minus 3 to the y values. Or this minus 3 is going to be a vertical. Let's retype that, vertical translation, which is the y values. Okay, other things we should know is horizontal translations are going to do the opposite of what they look like. So although this says plus 2, it's actually going to move to the left 2 units. And that's because this function is in terms of y. The x is not isolated. Okay, whereas this vertical translation does what you think it does. It moves down 3 units. Okay, and these definitions here are the key to moving this whole function. So if I look at the graph, what should happen is it goes left 2 units, 1, 2, and then it goes down 3 units. So for example, this point here would go over 2, and then down 3, and would wind up over here. Okay, every point on this graph would do the same kind of thing. So you'd get a new translated graph, that started to look something like this. Now, I don't want to just sketch a graph. I want to do this a little bit more accurately, but by defining the transformations first, you should know if your graph looks correct or not. Okay, in order to do this more accurately, I'm going to apply the transformation to each point. So for example, let's make a table here. So my table isn't going to be inputs, outputs this time. It's going to be original points versus translated points. And I'm going to transform each point individually, starting with -4, 0. Okay, if I want to take -4, 0, and I want it to go to the left 2 units, 1, 2, the new x-coordinate would be -6. Or you do -4 minus 2 is -6. Okay, now I also want it to go down 3 units. So like I said before, 1, 2, 3. Our new point's going to be here with a y-coordinate of -3. Okay, so that's how you would take the original point and translate it to its new location. We're again going to repeat this for every point on the graph. So if this point here is -3, you'll see those are labeled for you here, -2. Well, to go left 2 units, I'd be at -5. To go down 3 units, I'd be at -5. And I'm just going to repeat this process for every single point on the graph. Because one key piece of transformations is if some point on the graph moves, the whole function needs to maintain its same structure and move with it. So I'm just writing all the original points here, and I'm going to transform them the exact same way I did these two. I'm going to pause the video to do so. You can try this on your own, and I'll come back with the answer. Okay, if I didn't make any mistakes, these are the new transform points, assuming that you're moving left 2 units and down 3 units. What I'm going to do now is sketch a graph, and then we can get a visual of did it move the way we thought it would move. It's only translating or shifting, so it should maintain its same shape, just move left or right. Okay, so I'm going to go ahead and graph these points. You should do the same in your notes, and I'll come back with the answer again. Okay, here are those points plotted on a graph. So if done correctly, as I said before, it should maintain the same shape. So this one kind of has like a dipper here, and then it's got an upside down V. And as you can see here, it's got the same shape, right? So it's got a dipper here, and then it goes in that upside down V. It hasn't got wide or skinnier or anything. It just shifted to the left 2 and down 3 units. So we can check that and see that we've done the transformation correctly. Again, the main point is when you're reading this rule, whatever the rule looks like, even if it says to get h of x, you take f and then it's 2x. This is not an equation per se, but more of a rule of how that function is going to transform. So this says take the function f, and then you're going to apply some transformation to the x values. This time it's being multiplied or divided to the x. So it's actually going to change the width like a scale factor. Right, it makes sense when you add or subtract, it just kind of slides. But if you multiply, you're going to change the width or the scale factor, which we would call either a compression or a stretch. Okay, remember again, any transformation done to the x is going to do the opposite of what you think, because this function is in terms of y, not in terms of x. Okay, if you wanted to put it in terms of x and solve for x, you would have to divide both sides by 2. So that's the transformation that's applied to the x, is you're actually going to divide all the x values by 2. And if you divide all the x values by 2, okay, let's actually scroll back up here. Right, if I divide this x value by 2, what's once was here would now be here. Same thing here would now be here. So you're going to see the x values move in this direction, like you're squishing them horizontally. So this would be a horizontal compression or shrink, whatever word you like. I like the word compression because that like visually shows what you're doing. You smush the values together. In order to perform this horizontal compression, I'm going to do the exact same thing I said before. So I'm going to take the original points and I'm going to translate them according to that rule. And the only thing you're changing here is the x value because you're only dividing the x values by 2. So all these y values can actually just stay the same. So I'm just going to write those in real quick here. All the y values, whoops, not the x values, but the y values are staying as they were. And we're just going to divide all the x values by 2. So -4 divided by 2 would be -2. -3 divided by 2, yeah, it would be 3/2. That's okay. And this would be 1/2. Fractions never hurt anybody. Luckily, when you divide 0, it stays 0. 2 divided by 2 is 1. And 5 divided by 2 is 5/2. Again, fractions are okay. Most numbers in this world aren't whole numbers or integers. So now we're going to take these translated points and we're going to plot them on the graph. I'm encouraging you to plot on the same graph or on a different graph. It doesn't matter, but I'll come back with the answer in a second. Okay, this time I chose to throw it on the same graph. I'm going to highlight it here. So as you can see, it's got that same shape with a little dipper and then the V, but it's just gotten smushed horizontally. So again, this point is now here. This point is now here. It went this way and this way compressed, like you're squeezing it together. Okay, but the shape stays the same. It didn't reflect. All it did was get quote unquote skinnier. And that's a good way to check to know you've done it correctly. So we can do all kinds of transformations. I just gave 2 examples. Here are a couple more. I'm just going to go through and identify what these would do, and then I'll let you try to graph them on your own. So number 3 says to get k of x, you're going to take f of x, which again is kind of like y, and you're going to multiply it by 3 halves. Not just 3 halves, but negative 3 halves. Okay, so since this is directly attached to the function, these are going to affect your y values. Okay, and you're going to take all of your y values and you're going to multiply them by 3 halves. Well, really by negative 3 halves, which is negative 1.5 for the record. Okay, so if you take a y value and you multiply it by 1.5, it's going to get taller. So for example, if you take 2, multiply by 1.5, it's going to give you 3. So if the y value was here, it's now going to be here. It's going to get taller on the y-axis. Okay, but not only are you going to multiply by 1.5, you're also going to multiply it by a negative. So really you're making all the y values negative. For example, if your y value was 6 and you multiply it by negative, it's going to come down here and be negative 6. Or if your y value was 4, it's going to be at negative 4. Or if your y value was already at negative 2, it's going to become positive 2. So you'll notice each of those points I drew reflects over the x-axis. So in conclusion, there are 2 transformations happening here, even though you can do them at the same time. So by multiplying by negative 3 halves, let's write that in, it's going to first, well, not necessarily in any order, it's going to reflect over the x-axis because all your y values are going to become negative. And also it's going to vertically stretch by a factor of 1.5. So not quite 2, but like 1.5 times as big. Okay. In a moment, I'll have you plot those, but first we're going to look at k of x. How would k of x transform? Okay, the 1 in here, again, we've already looked at in that first problem. So you're subtracting 1 from the x, but remember that does the opposite. So you're really going to add 1 to all the x values, which is going to be a horizontal translation. Horizontal, let's add on to that. Not just horizontal movement, but horizontal translation or slide. Okay, since this 3 is on the outside of the f of x, it's like being attached to the y or the outputs. So this is going to multiply the y values by 3, similar to the one we just talked about. So if a y value is at 2, it's now at 6. If a y value is 4, it's not at 12. It's going to stretch vertically. Let's try that one more time. Stretch. Okay. So with that said, I'm going to have you try both of these and plot them and see what they look like, and I'll come back with their graphs. Keep in mind, f of x is still this original function here. So f of x is the black lined graph. Take a moment. Okay, just starting with the graph from number 3, where you had the function being multiplied by negative 3 halves. You'll see this time it flipped upside down, which makes sense because all your y values were multiplied by negative. Second of all, you'll see it stretched out because it goes all the way up to 4.5 here, whereas on this one, it did not go that high in either direction. So it's been stretched out vertically. Again, getting that visual is a good way to check that you know what those values do to the function. Now I'm going to go ahead and graph 4, and again, I'll come back with the answer. So I'm going to multiply the y values by 3 and add 1 to the x values. Okay, last but not least, we're looking at this purple graph, which you can see shifted over 1 unit because it's no longer going through 0, 0, and way stretched out vertically because it got multiplied by 3, or the y values did. Here's a list of new points for you to look through, and that's several examples of how to transform functions. The easiest way is to interpret the rule and then transform 1 point at a time. You can do this on any function, or you can kind of do it as a whole and say this is how the picture moves. Have a good rest of your day.